It's one small step for man, one giant leap for mankind.
Space, the final frontier. As humans, we are all dead set on trying to achieve space travel. What we fail to notice, however, is that with such huge ambition comes an even larger set of challenges and costs to be able to even achieve them. This is best exemplified in the Apollo programs, which successfully landed astronauts on the moon. It is also known as the most well-known lunar projects, but its total cost has been estimated at around $25.4 billion US, which is equivalent to roughly $152 billion US in 2021, adjusted for inflation. This involves the spacecrafts used, the launch vehicles, development and operations done, as well as direct project costs as well. The main force that we need to deal with when trying to escape from the shackles of our planet Earth is its gravitational force. And to be able to escape from the chains of our gravitational force of Earth, we need to escape velocity. The escape velocity is the speed at which an object travels to break free from either the planet's or moon's gravity and leave without any development of propulsion. The speed at which it is required for a spacecraft to escape velocity is 11.6 kilometers per second, or 40,000 kilometers per hour. That is 11,600 meters per second, which is approximately 34 times the speed of sound. Here, the formula for escape velocity is shown clearly, where the VE stands for escape velocity, obviously. The G stands for universal gravitational constant. In this case, for Earth, it is 9.8 meters per second squared. For the mass of the body, we just plug in the mass of the Earth. And R is the distance from the center of the mass, which in many cases stands for the radius. So the main problem we face is that there is too much fuel and oxidizers required to send a simple amount of payload to space. Spacecrafts require a minimum of 977,166 pounds of fuel. This uses up tremendous amounts of fuel and metals. And many of the Apollo project spacecraft failed in escaping velocity, putting all that effort into waste. But what is interesting is the dilemma that engineers face when trying to design rockets and spaceships, as well as fuel compartments. Because as you try to add more fuel or more parts and metal pieces to better improve your spacecraft, you also have to increase the amount of fuel needed to be taken, which then in turn adds to the total mass of the spacecraft, which then turns into more energy having to be spent. And so the solution? We need to find an energy-efficient way to travel to space. This is where Skyhooks become the future of efficient space travel. Now, to understand Skyhooks, you need to understand tethers. Tethers are created when a cable and weight are connected to anchor something movable to a reference point which may be fixed or moving. A skyhook is a momentum exchange tether that aims to reduce the cost of placing payloads into low Earth orbit or into space. Well, now you might be asking, well, how can skyhooks be possible? Well, I'll tell you how. The counterweight holds a long cable in place while it rotates around a circle. A rotating tether slows down its tip relative to the ground at the bottom and speeds it up at the top like a catapult. You transfer energy from the tether and get a massive boost when released twice from the tether's rotational velocity. Xylon fibers are great for skyhooks as they are resistant to extreme temperature changes and tension force between the weight. To protect from meteorites, there could be a web of redundant fibers added to better protect the skyhook. There are extra questions that can be raised, especially about the momentum issues involved, because as more ships latch onto the skyhook and pull themselves up, they use up the momentum that keeps the skyhook in place. This would lead to the tether crashing down to Earth. However, there is a way to solve this issue, because skyhooks act as a form of a battery for orbital energy, because they balance the payloads coming back to Earth and leaving. This can help balance the momentum. Arriving ships bringing humans or materials can add energy to the tether, which it can give to other ships departing into space. This way, the tether never loses energy and is renewable. In short, the more skyhooks are used, the cheaper they get. But we're not only going to stop there. There's a reason why skyhooks are the future of space travel. Because we could have a set of tethers, one around Earth, one around Mars. They could make the trips between planets fast, straightforward, and low cost compared to rockets that need to use escape velocity all the time. Tethers could shorten the trips from 9 months all the way down to 5 or 3. As well as reducing the scale of rockets required by 84 to 96%. Over time, people could also travel using tethers in relative luxury, as we could now afford to invest in passenger comfort. But this could go much further than simply Mars. We could go past the asteroid belt and towards the moons of the gaseous planets, which are mainly solid, and set up even more skyhooks. Skyhooks could become our way of energy-efficient interplanetary transport. And this is why skyhooks are the future of energy-efficient space travel. Thank you.